Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is a Bronsted-Lowry acid? Okay. Bronsted-Lowry acid. So the Bronsted-Lowry acid's definition is a species that donates a proton. So a proton can also be referred to as an H+. And on the other hand, we can have a Bronsted-Lowry base. As you can guess, this is a species that accepts a proton. Okay, so let's write down an example of a Bronsted-Lowry acid and base. So let's say we had HCl reacting with water to form H3O plus a chlorine ion. In this case, our hydrochloric acid acts as our Bronsted-Lowry acid. And this means it donated one of its protons to the water, which makes our water the Bronsted-Lowry base. And the products of this reaction was H3O plus and Cl minus. So this means that H3O plus is our conjugate acid, and Cl minus is our conjugate base. And the reason we name these products conjugate acid and conjugate base is because if this reaction were to be in reverse, then H3O plus would be the one to donate one of its protons to the chlorine ion, becoming the new acid, and the chlorine ion accepts one of the protons and it becomes the base. So this is the reason why we call these the conjugate acid and the conjugate base. And the junior tutor said that Bronsted-Lowry acid is described by Johannes Nicolas Bronsted and Thomas Martin Lowry, wherein species that give off its proton, H+, to a proton acceptor, or Bronsted-Lowry base. This is proposed in order to overcome the Arrhenius theory about acids and bases, which is only for aqueous media. Okay, so the solution is correct. Okay, question 2 asks, what is chemical energy? And also gives some examples. Okay. So even just analyzing the word chemical energy, we can kind of get a feel about what it might mean. So chemical energy is the energy that is stored in the bonds of chemical compounds. And they can be released through the form of heat and I'll just start to list off some common examples of where we might find chemical energy in real life. So for example, petroleum is a source of chemical energy. We use petroleum to fuel our cars to give it energy in order for the cars to run. Another example is photosynthesis. Plants get their food source, I'd say, from light, and then through photosynthesis, they can store all of this energy, and that's how they use it to grow. Even batteries, which run on different reactions, especially redox reactions, that also give off energy. For example, you can have the oxygen reduction reaction where it uses oxygen and it produces byproducts like water, and as a result, energy can be formed in that way. Even natural gas can be a source as well. And let's see what the junior tutor said. Chemical energy refers to the energy stored in the bonds of chemical compounds. Chemical energy may be released during a chemical reaction, and examples of sources of chemical energy are coal, wood, biomass, food, photosynthesis, natural gas, cellular respiration, chemical batteries, petroleum, and propane. Yep, so the solution is correct. Okay, question number 3. How many valence electrons does an oxygen atom have? Okay, so let's think about an oxygen atom. If we were to look it up on the periodic table, we'd see that oxygen has an atomic number equal to 8. So this tells us that there are 8 protons in an oxygen atom. And it also tells us that if our oxygen was a neutral compound, then we also have 8 electrons in an oxygen atom as well. Just to balance out the charge of the 8 protons, we would also have 8 electrons. So now that we know that oxygen has 8 electrons, we can try to sketch out an electron diagram showing all of those electrons in oxygen. So there are 2 in the innermost shell, And then now that I know that I wrote down 2, I need 6 more in an oxygen atom. So let's just draw 6 in the next shell. And this is kind of like a picture of an oxygen atom. So when we refer to the valence electrons, these are the electrons in the outermost shell. So if we look at the oxygen atom diagram that we drew, there are 8 electrons in total, but there are only 6 in the outermost shell. So therefore, we can say that oxygen has 6 valence electrons. Okay, so let's see what the junior tutor said. Oxygen has 8 electrons, and 2 electrons are in the first energy level, occupying a spherical orbital. So that's also known as the s orbital. And the 6 electrons are in the second energy level, the outermost energy level, since this level can accommodate 8 electrons. So 2 in an s orbital and 6 in the p orbitals. Hence, oxygen has 6 valence electrons. Okay, so the solution is correct. Okay, so question 4 is a polarity question explaining why SO2 is a polar molecule, whereas SO3 is not. Okay, so let's try to draw out the Lewis structures of both SO2 and SO3. Go down a bit. Okay, so let's find out how many total valence of electrons SO2 has. So SO2 contains a sulfur that has 6 valence electrons and 2 oxygen atoms that also have 6 valence electrons. So if we add it up, we have a total number of 18 valence electrons in SO2. So now if we draw out our Lewis structure, sulfur will be our central atom, and I'll just draw 2 single bonds to oxygen. And these oxygens may have a double bond. And then I'll just show the 2 pairs of lone pairs on each of my oxygen atoms. So now let's count out how many atoms I've drawn so far. Each bond contains 2 electrons, and we have 4 bonds, so that's 8. And then each oxygen has 4 valence electrons, so that's also 8, so we have 16. So I just need to put 2 more electrons on my central sulfur atom. So now let's analyze the shape of this molecule. So the central sulfur atom contains 1 lone pair, and it contains 2 bonded atoms. If we were to look up the molecular shape of this molecule, we can use the Vesper table and find out that when you have 1 lone pair and 2 bonded atoms, you have a bent molecular shape. So I'm just going to say bent. And what we also need to calculate is the electronegativity difference between a sulfur atom and oxygen. So electronegativity difference is a big aspect of how one can find out whether or not a bond is polar or not polar. So let's look at the electronegativity difference. So sulfur has an electronegativity of 2.5 and oxygen's is 3.5. So let's put 3.5 minus 2.5. So the electronegativity difference is 1. And the reason why I calculated the electronegativity difference is because when we have a polar bond, then your electronegativity difference is greater than 0.4, but less than 1.69. So what this tells us is that because the difference in electronegativity between sulfur and oxygen is 1, then that means there's going to be dipole moments pointing towards the direction of the oxygens. Kind of like that. So we have a net dipole moment in the molecule going this way, meaning we have partially negative charges and a partially positive charge where the sulfur is. So notice that these dipole moments aren't able to cancel each other out, and the reason why is because of the bent shape in the molecule. So this means that SO2 is polar, and I'll say that dipole moments don't cancel. Okay, so now that we did SO2, let's look at SO3. Again, we're going to find the total number of valence electrons of SO3. Sulfur has 6, and this time oxygen has 3. So we have a total number of 24 valence electrons. So now let's draw sulfur as our central atom, and then the 3 oxygens bonded to the sulfur. And I'm also going to draw in double bonds. And all of the lone pairs. And now let's calculate how many electrons I've drawn so far. So each bond has 2 bonding electrons. There are 3 bonds. Well, 6 bonds actually. So that's 12. And we have 4 lone pairs on each oxygen. So that gives us 24 electrons in total. So already we don't need to add any more lone pairs on the sulfur. We already have our 24 electron count in this structure. So let's find out its molecular shape again. So this time sulfur has 0 lone pairs. And we have 3 bonded atoms. So now let's look at our Vesper table to find out what kind of shape it has. So when we have 0 lone pairs and 3 bonded atoms, this means we have a trigonal planar molecular shape. So therefore, trigonal planar. So we don't need to calculate the difference in electronegativity since we already did that previously, but I'll just recall that the difference in electronegativity is 1. So again, you're going to see the same dipole moments going towards the direction of the oxygens. But now you'll see this time there's no more lone pair on the sulfur, so all of these dipole moments will cancel each other out. So therefore, we can say that SO3 is a nonpolar molecule. The dipole moments cancel each other out. Okay, so now let's see what the junior tutor said. SO2 is a polar molecule. Polar molecule is a molecule in which the distribution of electrons between the bonded atoms is uneven. That is, one molecule is slightly positive while the other molecule is slightly negative. To determine whether a molecule is polar, the electronegativity difference between sulfur and oxygen can be compared, which is a measure of tendency of an atom to attract electrons of a bond, and they can be seen on the periodic table elements. Well, sometimes. And from the periodic table, the electronegativity of sulfur is 2.58, while for oxygen, it's 3.5. So from this, we can see that there's an electronegativity difference between the sulfur and oxygen atoms. So that's greater than 0.4. So this causes an uneven distribution of electrons and makes sulfur dioxide a polar molecule. The Lewis structure of SO2 is shown below. Okay, so they got the same structure, and it can be seen that there's an unbonded pair of electrons on top of the sulfur. This makes SO2 to have a net dipole moment. For SO3, it is nonpolar. It has equally shared electrons between the atoms in a molecule. Not really, they still have an unequal share of electrons. It's just that they are arranged symmetrically that makes the dipole charges cancel each other out. Note that there's an electronegativity difference between sulfur and oxygen atoms. However, its net dipole moment is 0. You can see it's a symmetrical molecule that is trigonal planar. And that is why SO2 is polar, whereas SO3 is nonpolar. Okay, so this solution is correct. Okay, so question number 5. We have the potential of Fe2 and Fe equal to negative 0.44 volts. And for the silver plus to silver, it's 0.8 volts. So part A is to calculate the standard cell EMF of a galvanic cell that has been constructed from these species. And B, can you use an iron spoon to stir a silver nitrate solution, and why? Okay, so for this question, let's first show out, we'll show our oxidation reaction and our reduction reaction. So for the oxidation reaction, this is when the species increases in its oxidation number. And it also typically has the lower reduction potential. So the lowest value is the negative 0.44. So therefore we can say that for this, let me make room. The oxidation reaction would be with the iron solid to iron 2 plus 2 electrons. So notice that the iron went from oxidation number of 0 to 2 plus, so it got oxidized. And also, the oxidation reaction occurs in the anode. So we can label this as the anode. Which is equal to negative 0.44 volts. So now let's do the same thing for our reduction reaction. So for the reduction reaction, we have silver plus an electron, and the silver plus gets reduced to just silver. And we can write that the reduction potential of the cathode is equal to 0.800 volts. And this is because the reduction reaction occurs in the cathode. So now to answer the question, calculate the standard cell, which is E cell, of a galvanic cell that has been constructed from these species. So we can calculate E cell because this is equal to E cathode minus E anode. So E cathode is 0.800 volts, and E anode was the negative 0.440 volts. So when we subtract a negative number, that's the same thing as adding it. So E cell would be equal to 1.24 volts. Okay, so now let's do part B. Can you use an iron spoon to stir a silver nitrate solution, and why? Okay, so we can say that the iron is more reactive and we know this because Fe2 plus Fe is lower than that of silver's. So this means that silver plus will oxidize your solid iron to Fe2 plus. So therefore, the spoon will corrode in the solution. So no, you cannot use an iron spoon to stir the silver nitrate solution because the spoon will corrode. So now let's see what the junior tutor said. Part A, The standard cell EMF can be computed by adding the standard potentials of the oxidation half reaction and the reduction half reaction. Step 1 is to determine which species is reduced and which is oxidized. The reduction potentials given indicate the extent to which a species can be reduced. The more positive the value is, the more the species is reduced. So between silver and iron, the standard potential of silver is more positive, meaning that silver plus will be reduced, will be the reduction half reaction, and the iron 2 plus will be the oxidation. Chemical equation is given by the following. Yep. And now determine the chemical equation and E cell. Add the reactions and make sure to cancel the electrons to determine the galvanic cell chemical equation. Okay, so they also got 1.24. And now for B, can you use an iron spoon to stir? It cannot be used because the iron is more reactive than silver. This would mean that upon the contact of the iron spoon, the silver ions will be easily displaced by the iron ions as given by the reaction. So they give the reaction as well. So this solution is correct. Okay, so now we're on question number 6. What is the molar mass of KHP? So KHP, it's not just like potassium, hydrogen, and phosphorus. It's actually an acronym that stands for potassium, hydrogen, phthalate. I think this pH is silent. And I can draw out the structure of KHP. It's basically like this benzene ring. That has like a carboxylic, like potassium group. And also just a carboxylic acid group. Like that. So the chemical formula for KHP is C8H5KO4. Okay, so now to find the molar mass of KHP, we need to find the different molar masses of all of the atoms involved in KHP. And to do that, we would just look up their values on the periodic table. So the molar mass of KHP is equal to 8 times the molar mass of carbon, since there are 8 atoms of carbon in KHP. Similarly, we do 5 times the molar mass of hydrogen, plus the molar mass of potassium, plus 4 times the molar mass of oxygen. Okay, so looking their values up on the periodic table, carbon has a molar mass of 12.01. Hydrogen has a molar mass of 1.01. And potassium has a molar mass of 39.10. And lastly, oxygen has a molar mass of around 15.99. Okay, so adding all of these values up, we get a final molar mass of KHP to be equal to 204.22 grams per mole. Okay, so now let's see what the junior tutor said. The molecular formula of KHP, potassium hydrogen phthalate, is C8H5KO4. Molar mass of KHP, 8 times molar mass of carbon, 5 times molar mass of hydrogen, plus molar mass of potassium, plus 4 times the molar mass of oxygen. So they also got 204.22 grams per mole. So this solution is correct. Okay, so question number 7 says to draw the products of the following reaction. So we have this compound. We draw the full compound. So there is a double bond to a nitrogen. And it reacts in acidic media, HCl, and water. Okay, so when we have this imine in acidic media, the reaction is called an imine hydrolysis. Okay, so let me show the mechanism for this reaction. So first we have the lone pair on the nitrogen come in to abstract this proton, kicking off the chlorine. And we're left with this protonated nitrogen group that has a positive charge. And it still has that ethyl group sticking out. And what happens next is one of the water molecules will come in and try to relieve that positive charge by attacking this carbon here and reducing that double bond. So now we have a single bond here. The nitrogen. And we have a newly formed oxygen bonded with the carbon. And it is positively charged. So to relieve that positive charge, my drawing's kind of cut out. Let me just move this hydrogen down. Okay. So to relieve that positive charge, the lone pairs on the hydrogen will come in, take one of the protons, bringing electrons down to the oxygen. And now we have another positively charged nitrogen that has the two hydrogens bond there, And you can already see that there is now an oxygen group, well, an OH group that has now been formed. And this part stays the same. This is positive. And what happens next is another water molecule comes in and takes one of the hydrogens from the alcohol group, forming a double bond here, and it kicks off this entire positively charged nitrogen group. So now we are left with our final products, which is this aldehyde and also this amine salt. So we can name these compounds. So I'll just say this is an amine salt. And let's name this compound. It is a 3-carbon chain that has an aldehyde group and a methyl on carbon 2. So this is called 2-methyl propanal. Okay, so these are our products after the hydrolysis reaction. And let's see what the junior tutor said. The given reactants are an imine and an aqueous acid. When these two undergo reaction, the carbon-nitrogen double bond of imine will be cleaved to produce an aldehyde and an amine. Scheme 1 shows the mechanism by which the hydrolysis reaction proceeds. Okay, so for part 1, it shows the nitrogen's lone pair taking the proton of this protonated water. So this can also occur as well. So for mine, I just had it taking one of the hydrogens from HCl, but this can happen as well. Since it's HCl and water, we're going to have protonated water groups. And now the second step is a water molecule coming in to attack the carbon and relieve the positive charge on the nitrogen. And then another water molecule comes in and takes in one of the hydrogens. And they have the lone pair taking a proton. And then they have another water coming in to take the hydrogen from the alcohol group, forming the aldehyde and forming H3O+. And then they have their final products. Okay, so basically, since the mixture will be acidic, the nitrogen atom will be protonated, thereby producing the iminium ion. This iminium ion will be attacked by water via SN2 reaction, followed by proton transfer and the elimination of the amine group, formation of the CO double bond of aldehyde. And note that although amines are bases, it will appear as a protonated ion in the acidic reaction mixture since it's considered a weak base. Okay, so that's another thing. And with these, it can be concluded that the organic products of the given reaction will be 2-methyl propanal and ethylamine. Okay, so this solution is correct. Okay, so on to question 8. cyclopropane C3H6 reacts to form propene in the gas phase. The reaction is first order in cyclopropane and has a rate constant of 5.87 times 10 to the negative 4 inverse seconds at 485 degrees Celsius. If a 2.6 liter reaction vessel initially contains 725 torr of cyclopropane at 485 degrees Celsius, how long will it take for the partial pressure of cyclopropane to drop below 104 torr? Okay, so this question tells us a lot of things. It tells us that we have a first order reaction. And because we know that this is a first order reaction, then we can write down the first order integrated rate law. So there are different types of rate laws. You can have second order and third order as well. But in the case of our question, we have a first order rate law. So this tells us that we can write down this equation as ln of the pressure at time is equal to negative kT plus ln P naught. So I'll define what each of these variables mean. So P sub T is the pressure at time T. And we have K. So K is our rate constant. So this was given in the question, which was 5.87 times 10 to the negative 4 inverse seconds. And next we have P naught. And this is just initial pressure. So before the reaction takes place. Okay, so we know that the reaction vessel initially contains 725 torr. So we can say that the initial pressure is 725 torr. And we know that the pressure at time t, which is what we're trying to solve for, is equal to 104 torr. So now all we have to do is plug in our variables, or plug in our values and solve for the unknown, which is time. So how long will it take for the partial pressure to drop below 104 torr? So now let's plug in our values. We'll have ln of 104 is equal to negative K, which is the 5.87 times 10 to the negative 4 inverse seconds times T. I didn't give myself enough room, but let's just continue it here. Plus ln of our initial pressure, which is 725 torr. Okay, so now let's try to simplify this. So when we take the ln of 104, you get around 4.64. Negative 5.87 times 10 to the negative 4. And when you do ln of 725, it's around 6.586. Okay, so now let's just try to solve for t. 4.64 minus 6.586 divided by negative 5.87 times 10 to the negative 4 inverse seconds is equal to t. Plugging that all in, we get t is equal to 3,308 seconds. And we can just convert this to minutes, which is like 55 minutes. Okay, so it will take 55 minutes for the partial pressure of cyclopropane to drop to below 104. Okay, so let's see what the junior tutor said. A first order reaction means that the rate of the reaction is linearly dependent on the concentration of pressure of the reactant. This is described by the equation below, which is referred to as the first order rate law equation. Since the reaction is in gas phase, the equation is written in terms of pressure. Rate is equal to K times the pressure of gas A, where K is the rate constant for a first order reaction. The unit is time inverse of time. So this equation can be converted to the equation below, which is known as the first order integrated rate law expression. Okay, so they have the same equation, pressure of gas A after time, the rate constant, time elapsed since the start of the reaction, and the initial pressure of gas A. So using this, we can calculate the time required for the pressure of cyclopropane to drop to 104 torr. And they got 3,308 seconds. So this solution is correct. Okay, so question number 9. Calcium chloride, or CaCl2, is an ionic compound in which, and then I'm guessing we just need to pick the correct answer. So let me write down calcium chloride. And we know that this is an ionic compound because it is a metal and a non-metal. So we can separate calcium chloride into its ions, which might help us understand the question better. So basically, calcium chloride was formed because a calcium 2+ ion reacted with 2 negatively charged chlorine ions. So basically, we can say that the calcium gives away 2 of its electrons to the chlorine in order to form the ionic bond. So for A, it says each chlorine atom has lost electrons. So we know this isn't true because chlorine has a negative charge. So that means it actually gained electrons. So that is not correct. B, one chlorine atom transferred an electron to the other chlorine atom. So we know that's not true either because chlorine is looking to accept electrons. You won't find one of them giving an electron to the other for this question. C, calcium has 2 extra electrons in its innermost shell. So calcium does, in its innermost shell. So we know that's correct because calcium should have the 2 extra electrons in its outermost shell. So C is incorrect as well. D, calcium has lost 2 electrons. So D is actually true. And let's look at E just because calcium has gained 2 electrons, so that is false as well. So therefore D, calcium has lost 2 electrons is the correct answer. So now let's see what the junior tutor said. D, calcium has lost 2 electrons. Calcium chloride is an ionic compound, therefore the subscripts are crisscrossed. Hence, the +2 in calcium means it gives up 2 electrons. Okay, so this solution is correct. Okay, so question number 10. What is the compound name for HClO3? Is it hycrochlorous acid, chlorate acid, perchloric acid, chloric acid, or I think that's supposed to be hypochloric acid? Okay, so the name of HClO3, let me write it down here. HClO3 is known as chloric acid. So this is answer D. And let's compare the compounds, like the different compounds that would give off some of the other answers in the question. So when there is 1 less oxygen and we have HClO2, this is known as chlorous acid. And when we have another oxygen additionally lost, this is known as hypochlorous acid. And if we were to add another oxygen to be HClO4, this is called perchloric acid. And obviously, when we have everyone's favorite acid, HCl, this is just called hydrochloric acid. So you can see how the names kind of vary in this way. When you add an additional oxygen, it has the prefix of hypo and it ends in -us. When you add an additional oxygen, it still has that suffix ending in -us. With O3, it ends in -ic. but if we were to add an additional oxygen, it still ends in ic, but it has per as the prefix. So it takes some like getting used to, but the more practice you do in naming compounds like this, then the easier it gets. So I myself I haven't done a lot of this in a while. It's a bit rusty, but those are basically all of the acids here, with the exception of chlorate acid, which I don't think exists. So the rest are real acids. And the junior tutor said that generally, in the case of an acid that is formed from just hydrogen and another element, it is named as hydroelementic acid. For acids that contain hydrogen, another element, and oxygen, these are called oxyacids. You do need to be familiar with some ion names. So ClO3 minus ion is known as the chlorate ion. If an ion name ends with 8, the acid is named by replacing 8 with ic. If the ion name ends with ite, then the acid is named by replacing ite with us. Hence, HClO3 is named chloric acid. Okay, so this solution is correct. Okay, so question number 11 is to determine the bond order for F2, F2 plus, and F2 minus. Which molecule should be the most stable? So to answer this question, I'm going to draw the molecular orbital diagram, and I'll do it for F2, just so that it'll be easy for us to compare what happens if it gained an electron and what happens if it lost an electron. Let's try to draw this molecular orbital diagram. So the highest in energy in terms of the orbitals for F2 would be the sigma star orbital in 2p. Below that is the pi star in 2p. And then the star signifies that these are anti-bonding orbitals. And when there is no star, these are known as bonding orbitals. So here is just regular pi orbital of 2p, and then just a regular sigma 2p orbital. And then on the left and the right sides, I can also show where these orbitals came from. So this is the 2p orbital. And then you kind of just draw dotted lines to show that these are from 2p. Okay, so now let's do the same thing, but for the 2s orbital. So below the 2p, we write 2s. So we have the anti-bonding sigma star of 2s that is higher in energy than the sigma 2s. And again, we can show where the electrons will come from, the 2s orbitals. And below that is 1s. So notice that for both 2s and 1s, there are no pi bondings that occur. And then finally, it's just the 1s bonding and anti-bonding. And then I'm going to show these on the side. So hopefully I have enough room to even like take notes for this question, but I'll try to fit it on the right side. Okay, so this is basically our skeletal structure, you can call it, of the molecular diagram of F2. So all we need to do is fill in the electrons. So if we think about F2, so I'll write it here. F2 contains (18) electrons in total. So 9 of them come from one fluorine, and then the other 9 come from the other fluorine. So if I were to fill in all of the electrons, you can think of the left and the right sides, like the 1s, 2s, and 2p, just to be like a separate fluorine atom. So if I were to fill in that orbital filling diagram and put the electrons in, I can put the 9 from this. 1, 2, 3, 4. And our 2p should have the 3 orbitals here. Because a p orbital can hold 6 electrons. So that's why we need 3. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that's from one fluorine atom. And then for the second fluorine atom, I'll do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now that I filled in both of my individual fluorine atoms, now we can see where the electrons will come in and fill up all of the sigma and sigma star and pi star orbitals in this molecular orbital diagram. So since we have 18 in total, I'm just going to fill in the electrons the same way you would with opposite spins. So 1, 2, 3, 4, 5, 6, 7, 8. So I need 18 in total for F2. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So notice that when I have 18, then it stops at the pi star orbital. And now we need to calculate the bond order. So I'll write down the equation of bond order. I think I can just fit it down here. So bond order is equal to the number of electrons in the bonding orbitals minus the number of electrons in the anti-bonding orbitals. Divided by 2. Okay, so this is the equation for bond order. Just put this in a little cloud to separate it. And now let's calculate the bond order for F2. The number of electrons in the bonding orbitals are the ones that are in all of the sigma and pi that doesn't have the star. So let's count it out. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 10 in the bonding, and in the anti-bonding, which is the ones with the star, we have 1, 2, 3, 4, 5, 6, 7, 8. We have 10 minus 8 over 2, which is equal to just 1. So now let's see what happens if we were to gain an electron. So let's do this in green. If we were to gain an electron, then we would have, not gain an electron. F2 plus means we lost an electron. Because it's positively charged, we lost 1 electron. This means we now have 17 electrons in total. So it's going to look the same as our F2, except this time we lost an electron. So let's say in the green is F2 plus, and we lost an electron there. Let's try to calculate that bond order. The number of electrons we have in the bonding will still be 10. But this time, the number of electrons in the anti-bonding, we took out 1. So now we have 7. So 10 minus 7 divided by 2 is equal to 1.5. And with that same approach, we can find out what happens if F2 gained an electron. So now we have 19 electrons in total. And I'm just going to draw an orange electron up here. So now that we have an extra electron in the sigma star, and it'll look like this in our other 2 orbitals. So now let's calculate the bond order of F2 minus. So now the number of electrons in the bonding orbitals is still going to be 10. But this time in the anti-bonding, there's going to be 9. Divide that by 2, we get 0.5. Okay, so back to the actual question. We determined all the bond orders, but now we need to know which molecule is the most stable. So I'll have a little explanation here. Stability is proportional proportional to bond order. So that means the higher the bond order, the more stable the compound is. So therefore, F2 plus is the most stable. Since its bond order was the 1.5. So now let's see what the junior tutor said. Bond order is given by the number of electrons in bonding molecules minus the number of electrons in anti-bonding divided by 2. And they tried to write out the molecular orbital for F2. So you can see it's sigma 1s, sigma 1s star, sigma 2s, sigma star 2s, and so on. And then, so then they showed that there are the Yep, so this is right. Bond order is equal to 1. For F2 plus, you can see that 1 electron was removed, and they got a bond order of 1.5. And when you gained an electron, there's now an electron in the sigma star 2s orbital, and its bond order was 0.5. So bond orders that are whole numbers are more stable than fractions. Therefore, F2 is the most stable among the three. So I'm just going to say that the solution is correct. I can also just mention that stability can be shown as proportional to bond order, making F2 plus the most stable. But I'll still mention that this solution is correct since they did give all of the different bond orders. Okay, so now we're on to question number 12, which is a multi-step question. So we have acetone or propanone has a density of 0.786 grams per milliliter, and the heat of combustion is 428 kilocalories per mole. Part A is to write the equation for the complete combustion of propanone. B, how much heat in kilojoules is released if 2.58 grams of propanone reacts with oxygen. C, how many grams of oxygen gas are needed to react with 15 milliliters of propanone. And D, how many liters of carbon dioxide are produced at standard temperature and pressure in part C. Okay, so this is multi-step, and it's a very good question because it covers a lot of different topics. So first, let's try to tackle just the first question, which is to write the equation for the complete combustion of propanone. So to answer this question, we need to first know the structure of propanone so that we can balance it. So propanone, if we analyze the name of this compound, it has a prefix of prop, which tells us that there are 3 carbons in the parent chain, and we know that it ends in -one, so that means the middle carbon will contain a ketone group, which is that double bonded oxygen, and then the rest of the bonds of the other 2 carbons will just be filled with hydrogens. Okay, so this is the structure of propanone. And if we were to write out its chemical formula, it would be C3H6O. Okay, so now that we have the chemical equation and we have the structure, when we have a combustion reaction, this means that the propanone will react with oxygen, and the products that are formed are water and CO2. Okay, so this is a combustion reaction, and now we just need to balance out all of the atoms. So let's do carbon first. So carbon, on our reactant side, there are 3 carbons, so we just need to put a coefficient of 3 in front of CO2. And now let's balance out the hydrogens. So we have 6 hydrogens in propanone, so we just need to put another 3 in front of H2O. And at this part, I like to now balance my oxygens. And I do it last because if I were to balance it first, then it would, once we start balancing the hydrogens and the carbons, then the numbers will all change and we have to redo it. That's why we balance oxygen last. So on our product side, we have 3 plus 6. So that is 9. And we already have 1 oxygen in propanone, so we need 8 more. So we just need to put a 4 in front of O2 to balance out the equation. Okay, so this is part A. We have our balanced chemical equation for the complete combustion of propanone. Now for part B, we need to know how much heat in kilojoules is realized if 2.58 grams of propanone reacts with oxygen. Okay, so to answer this question, we just need to do some calculations. So we know the mass of propanone is 2.58. And they gave us in the question that the heat of combustion is 428 kilocalories per mole. So let me write that down. Delta H of combustion is equal to 428, and the units are kilocalories per mole. So to calculate how much heat is going to be realized, we need to find out the number of moles in 2.58 grams of propanone. So let's recall that to calculate for number of moles, it's going to be mass over molar mass. So to find number of moles, we need to first find the molar mass of propanone. So we can do that down here. We know that the molar mass is going to be 3 times the molar mass of carbon plus 6 times the molar mass of hydrogen plus just the molar mass of oxygen. So we can find these different molar masses on the periodic table. So for carbon, it's 12.01 grams per mole. And for hydrogen, it's 1.01 grams per mole. And for oxygen, it's 15.99 grams per mole. So now if we add these all up, we get a final molar mass of 58 grams per mole for propanone. And now we can find the number of moles. So number of moles is mass over molar mass. So it's just going to be 2.58 grams divided by 58 grams per mole. So now we get a number of moles of 0.44. Now that we have our number of moles, we can solve for the heat. So heat is equal to the number of moles, which is 0.44, times the delta H of combustion, which is 428 kilocalories per mole. And then we end up with 19.04 kilocalories. So the moles will cancel out. And to convert to kilojoules, we just need to multiply by the conversion factor, which is 4.184 kilojoules per kilocal. So now our final answer is 79.66 kilojoules. Okay, so that's part B. Part C, how many grams of oxygen gas are needed to react with 15 milliliters of propanone? So they give us the density of propanone. So part 1 of this part C is to first find the mass of the propanone in 15 milliliters. So if we recall that density is equal to mass over volume, then we can rearrange this equation to solve for mass, which is density times volume. And the density was 0.786 grams per milliliter, and the volume was 15 milliliters. So this gives us a mass of 11.79 grams of propanone. I'm going to do it in a different color just so that it's more organized. But for the second step, we're going to find the number of moles of propanone. And again, we do number of moles is equal to mass over molar mass. So it's 11.79 grams. And we know the molar mass already is 58 grams per mole. So now to calculate for number of moles, we end up dividing and get 0.2 moles of propanone. And from there, we can also calculate the number of moles for oxygen. I'm just going to add that here. Then use mole ratio. So because we already balanced our equation, we know what the mole ratio between propanone and oxygen is. So we know that 4 moles of O2 is needed to react with 1 mole of propanone. So we just need to multiply 0.2 by 4. And we end up with 0.813 moles of oxygen. And now step 3 of part 3 of this question is just to find the mass. Find the mass of oxygen. So now mass is equal to number of moles times molar mass. Number of moles we found in the previous step to be 0.813 moles. And the molar mass of O2 is 32 grams per mole. So we get a final mass of 26 grams of oxygen needed. Okay, so let's start a new page and answer part D. Which is how many liters of carbon dioxide are produced at standard temperature and pressure in part C. Okay, so when we have standard temperature and pressure, that means that the temperature and the pressure, they're all constant. So the only thing that changes or that varies for this reaction would be the volume and also the number of moles. So at STP, the molar volume value is 22.4 liters. So at standard temperature pressure, volume is equal to 22.4 liters, and also number of moles is equal to 1. So we can just multiply 22.4 liters by the mole ratio of 3 moles of carbon dioxide. And we got that from the balanced chemical equation. There are 3 moles of carbon dioxide for every 1 mole of propanone. So 22.4 liters times 3 is equal to 67.2 liters. Okay, so now let's see what the junior tutor said. Step 1 is to write the equation for the complete combustion of propanone. And let's go back to mine. We have C3H6 plus 4O2 makes 3CO2 plus 3H2O. Step 2 is to find the heat in kilojoules of propanone. So they calculated molar mass to be 58. And then they just showed how so they showed that 58 grams. It's another way of showing that 58 grams of the propanone will produce the 428 kilocalories per mole. So 2.58 grams of propanone produces 19.04 kilocalories per mole, which is also around 80 kilojoules. Step 3 is to find the mass of propanone in the 15 milliliters. So they got 11.79. And then by using molar ratios, calculate the mass of oxygen. Yep, so they also got 26 grams. And then step 5, find the liters of carbon dioxide. We have 3 times molar volume, which is 22.4, and they got 67.2 liters. Okay, so this solution is correct. Let me just read this question again. Yep. I think I'm also going to answer part D using 15 milliliters of propanone. So the 22.4 is if it were like the molar volume of a gas. But if we did have 15 mils of propanone, no, I guess that's correct. Yeah, the solution is correct. Then I'll just add a note. Molar volume is equal to 22.4 liters. So which is why 67.2 liters of CO2 is produced. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a like and a comment, or you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.